Okay, morning. So this is lecture number 7, I believe. Hopefully you had a good 3 weeks break with some project work and doing some assignments and so forth. So we're now back to the lectures. Actually, there's only 2 more lectures, including today. So it's almost the end of the lectures now, and you will be looking forward to do a 3 weeks project afterwards. So so today we're going to talk more about the statistics tools, especially focusing on inferential statistics, which is mostly used for analyzing experimental results so that you can make conclusions and say interface A is better than B and so forth. So if you wind back a little bit, it was actually 2 lectures before when we did descriptive statistics, although it might have been almost 5 weeks ago. So statistics tools, there are basically 2 types of statistics tools that we mostly use in HCI research. And the first one we've looked last time was about descriptive statistics. And it's basically for describing the characteristics of the sample or the data you collected. So it's basically summarizing how the data looks like. So instead of reporting 20 people rated 7, 8, blah, 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 you can summarize it into kind of a couple of numbers that describes how people rated in overall, such as average or median or standard deviation and so forth, so that you can, instead of reporting all of the numbers that you collected through the users, you can report those couple of numbers describing what the collected data is. So that's why it's called descriptive. Inferential statistics, which we are going to cover today, is for making inferences. So that's why it's called inferential statistics. And it's basically making a prediction about the larger population, which is the whole user that's going to use your interface. But we cannot test the interface against the whole people or the whole population. So what we're doing is to sample some of the users and test it against them. And there comes the roles of the inferential statistics, which is making a generalization of based on the data you collected with the sample. It's making an inference about the total population or the whole user that you are expecting. So it's basically what it's doing is based on the samples and comparing the mean values of the 2 samples and doing some statistics around it based on probability functions, basically normal distribution, and then make a conclusion that with 95% of confidence we can say the 2 groups are different in the population as well, and so forth. So we're going to go through what kinds of inferential statistics there are and what kind of statistics you have to use depending on your experimental design. So depending on your experimental design, such as using within subject or between subject design, there are different tools that you'll have to use. So you have to be careful. And in the end, if you use different tools, sometimes it will the conclusion will be totally different. So you'll have to be aware of what kind of statistics tools there are and which statistics tool you'll have to use in which case of your experimental design. So a little bit reflecting what we've talked about descriptive statistics. This is basically the data set I've given you with the assignment. So what I was asking was basically based on the given data set, what kind of descriptive statistics you would like to report. And again, it depends on what scale the data set is using. So the first example was error in millimeters, which is kind of interval ratio data. And I said it was assuming normal distribution. And if you plot it, it's pretty much normally distributed. And in this case, you can pretty much report mean and the standard deviation. So if you report those two numbers, then the reader can basically replicate, although not fully, it can at least kind of replicate a similar set of data, which is, since the normal distribution is known and well-defined, if you just give mean and standard deviation, then you can pretty much
Just to get the same graph.
yeah, have the similar set of sample data. So that's pretty much enough. If it's not normally distributed, then you might consider reporting more information, such as which way it is skewed, or a little bit more simpler ways to just report the median, which will show if the median is closer to the mean, then it will mean it's pretty much symmetric. But if mean is towards one direction, then you can easily think which way it's skewed. And the second example was Likert scale, which is rating between 1 and 7. And usually, I think we've discussed this when we were talking about the questionnaires, and also when we were talking about descriptive statistics, that this is usually have to be considered as the word just got out of my, what was it? Not interval ratio, but ordinal data. Sorry. So 1 to 7, rating 1 to 7 has an order, so you can order them from 1 to 7. So definitely you can say 2 is better than 1. But the difference between the ordinal and the ratio or interval data was that we cannot guarantee the distance between the two levels are equal. So Likert scales, it's kind of under a little bit of a debate that some of the researchers still prefer to consider Likert scale as an interval scale, just for simplicity for sake. But recently, more of the researchers are agreeing that Likert scale should be treated as ordinal data. And for ordinal data, usually the median is the middle value that you might want to report. So I think based on my calculation, median is 6. So median is basically you sort all the numbers and then pick the middle one. If there is even number, then you have to average the center, the two numbers in the center. So if you...
Is it necessarily whole numbers?
Sorry?
Is it necessarily whole numbers?
And you can pick the midpoint. So if there is even number of samples, then you don't have the middle point value. So you just average the two numbers. So it's usually comes up with a whole number, integer number, or it ends up with 0.5. So you can report the median because since we cannot, for the ordinal data, we cannot, since we cannot make sure that the distance between the scale are equal, then you cannot really say, you cannot make the distribution kind of, you cannot guarantee that the distribution is unskewed. So even though if you plot it and it looks like a normal distribution, if you think of the scale are not equivalently distant, then you can easily think of that you cannot guarantee it's symmetric. So that's why it's better to report the median rather than the mean, because mean is more vulnerable to that skewedness, but median is mostly describing the center point of the whole data. So anyway, median is better one to report for ordinal data. And for ordinal data, since it's median, cannot really, it's better to report mean max values or interquartile values rather than the standard deviation, which is mostly comes with the mean, which is mostly useful for normally distributed samples. And the third example was nominal data, which is just naming the value. You cannot say which one is bigger than which or which one comes before which, but it's only describing which category it falls in. So it's sometimes called also categorical scale. And in this case, what you can report is the frequency, basically how many of A there are, how many of B there are, and how many of C there are. And the representative value you can report is the mode, which means the most frequent value. And in this case, it's actually not A. That's a typo. So it should be B. Sorry about that. So B is the most frequent value. So you can say if it was the question, if that data was collected by asking people which interface you prefer, then you can say most of the people preferred interface B. And instead of reporting the raw frequency value, such as 5, 8, or 3, you can also report relative frequency, which is basically a percentage of the whole from the whole number of sample. So that could be that could give a little bit more picture of how much of each choice was made out of the whole sample. So again, so you can report those values, and you can also plot different types of graphs, such as bar charts or pie charts in case of this type of nominal data set and so forth. But what you cannot really say is, even if you can report mean and standard deviation or other statistics for two groups, what you cannot really say is if that difference is meaningful. So say people using interface A made error of say 10 in average, and interface B made 12. You can see there's a difference of 2, but you cannot really say if that difference is really meaningful in terms of statistical way. So that's where inferential statistics are useful for. So again, it's making inferences about the larger population or the whole population based on your samples. So what you do is, in computer science way, the input for the inferential statistics is sample data, and the output is the conclusion about the population. And in many of the cases, it's about comparing the mean value of the two sample groups. So for example, if you had two groups of participants, one group using interface A and the other group using interface B, and you collected test completion time, then you put those test completion time you collected into an inferential statistics, might be a t-test. And then the outcome of the t-test will give you basically probability, which is basically called p-number, p-value or p-number. And that's the probability of rejecting the null hypothesis, which is most of the time saying the two numbers are not that different. And if that p-value is very low, then you can say, since the probability is very low, the null hypothesis, which is saying the two mean values are not that different, can be rejected. And you can say the two values are statistically significantly different. So we'll go into more details in the next slide. So, and if you call back what we've talked about at the last lecture, when we were talking about the hypothesis, there are basically two errors we can make when we are making decisions or conclusions out of the hypothesis. And if you think of, in reality, if H0 is true, which means there's no difference between the two groups, and if you conclude we reject the H0, then that's an error, and that's called type 1 error. And the probability of making that type of error is called alpha, and that's alpha value, which you will see later in many statistics tools, that you set this alpha value to very low number. And on the other way around, if H1 is true in reality, which means there's a difference between the two groups in real, but if you decide that you accept H0, which means you say there's no difference, then that's making another type of error, which is type 2 error. And the probability of making this type 2 error is called beta. And this is another value. But in many cases, statistics tools are more concerned about making false decision when there is no difference, but saying there is a difference, so which is basically type 1 error. So people more consider type 1 error is more serious, so people try to make this alpha value very low. So again, wrapping up, alpha and beta are kind of interrelated, but in the experimental research, it's generally believed that type 1 errors are worse because that's kind of admitting that you found a new finding, although it might not be true. So it's very trying to be conservative about new findings. Okay, so usually in HCI research or in more general, many of the researches use alpha level of 0.05, which is basically allowing only 5% of error when you say you find a difference when there is actually no difference. Okay. So if we recap how we do with hypothesis testing, we said about proving something is difficult than disproving. So the hypothesis, the way you formulate the hypothesis is to formulate the negation of what you really want to say, which is formulating a null hypothesis. So in this case, null hypothesis case could be, in most of the cases, it's written in a way that there's no effect of the solution, which means there is no difference between the interface, which means that the new design you made makes no difference and it's same as the old one, so it's no use. so that's the null hypothesis, which you want to reject with the statistics results. And basically what the inferential statistics tool does is to test if the difference is large enough that it's not because of the chance when you sampled the samples from the population. So it's basically reporting the probability value of that difference, where that difference came from. Is it because of actually the two interfaces are different, or is it because of the chance that when you sampled your participants from the whole population, there might be some probability that introduced that the mean value might appear different. So this p-value is basically meaning if this p-value is high, then that's saying the difference might have been occurred because of the sampling error, rather than the two interfaces are actually different. So if this p-value is low in the other way around, you can say the difference between the two mean value is not because of the sampling error, because the p-value is very low. And then you can, in that case, you can reject the H0, which says the two values are not equal. Then you can conclude, since H0 is rejected and false, then you can conclude the two groups or two interfaces have different level of difference.
As long as it's below 0.05, it's okay?
Yep. So it doesn't matter if it's 0.049 or 0.001 or whatever. It's just setting a kind of threshold. And of course it could be debatable. And in some cases, people tend to report something like almost significant when they find 0.051 or something value. But strictly speaking, that shouldn't be called almost significant. It should be not reported as not significant. Although you can still report the p-value so that you can give a kind of context to the readers that the p-value was close to 0.05. But still you'll have to conclude it's not significant. Then you can think of, if you don't want to conclude in that way, then you can think of other ways to improve it or reduce the p-value by introducing more samples, basically recruiting more participants and making the variance or the standard deviation a little bit more smaller so that it will eventually become more significant. But basically, this alpha level, which is the threshold of deciding whether the p-value is significant or not, is kind of convention to research, experimental researches, that people mostly agree that 5% is kind of low probability of making error. Sometimes if you want to go more strict, they also use 1%, which is 0.01. But in many cases, it's mostly 0.05 that we use in HCI. And again, even if you had very small p-value like 0.01, you cannot say it is more significant than having 0.04. Both are just simply significant because deciding if it's significant or not is based on the alpha level you set. So it's either one or either significant or not. You cannot.
But you can choose if you want to use 5% or 1%, can't you?
Yeah, you can choose 5% or 1%, or you can even choose 10%, like 0.1. It's up to you, but
How's that not saying that the one is more significant?
So you can choose the alpha level. So deciding significant or not, it's based on the alpha level you set. So if you set different alpha level, the p-value could be turned into a significant p-value could be turned into non-significant value. But again, so saying significant is relative to the alpha value you set. And alpha value, you can set 0.05 or 0.1 or even 0.1 if you want. But most of the researchers won't agree with you that 10% is enough for enough probability of making error. So in convention, as a society of scientists, most of the people, 0.05, which is 5%, is a kind of marginal level of p level that they want to make sure. And
So people only use the 1% if they get really good results?
So people, if it's a kind of if it's some research such as in medical application, they might prefer 0.01 because it might be critical for some health issues or safety issues and so forth. So they might prefer 0.01. But in many cases, it's mostly just 0.05. And it's, again, it's convention, and it's mostly a great value of being significant. And again, definition of significant itself is whether it's above or below alpha level. So it's nothing about being more or less significant. It's always about being significant or not significant relative to that alpha level you set. So that's how we do inferential statistics. So it's basically the input of the inferential statistics is, again, the sample data you've collected. And if you put into the inferential statistics tool, it will print out the p-value, which is basically saying if it's likely that you can reject H0 or not. But before you start doing statistical analysis, the inferential statistical analysis, it's better to get a feeling for the data. So it's many of the cases, it's better to try to see the descriptive statistics first, so you can feel and have a feeling of how kind of conclusion you'll be reaching. And it's especially important to check if your data is interval ratio data. It's also important to check if the samples are normally distributed, because depending on if it's normally distributed or not, the statistics tool you use might be different. Have to be different. And for doing this test, there is a test called Shapiro-Wilk test, and if you click there, there's a link that I've put on how to do this test using SPSS. Of course, you can use R or whatever tool you have and look for the test name the same. But anyway, there is a step-by-step guide how to do this, and it prints out, again, a p-value, whether it's normal or not. So So please have a read of this if you want to learn more details. Again, during today's lecture, I'm not going to go into details about how to do all these tests in SPSS or specific tool, but I'll provide some of the slides will have this kind of link that gives you a link to a website or a tool that you can go through step-by-step guide how to do those tests. So again, so in a nutshell, if you have interval ratio data, then better check if it's normally distributed or not using this kind of test. And because depending on the distribution, you might end up which tool you will use. And there are basically two groups of inferential statistics tools. And the first group is called parametric test. And this is the test that assumes the data you give to the test tool, statistics test, is assuming that the data is interval ratio and normally distributed. So if you're going to use this parametric test, you should make sure your data set is normally distributed. And if it fails, then you'll have to fall back into different method, which in most cases will be non-parametric test. So there is also another assumption that parametric test assumes, which is homogeneity of variance, which is basically meaning the two samples you have pretty much the same amount of standard deviation. So if you have two samples and you've printed out the standard deviation, and if it's one is very big compared to other, such as the first sample has standard deviation of 1 and the second has standard deviation of, say, 50, then that might be too much different. So in that case, you cannot really use the parametric test again. So again, to do that, there is a test called Levin's test. But in many cases, the statistics tools such as SPSS take care of this test as a part of doing running the parametric test. So you don't have to worry that much about this. So the reason why it's called parametric test is because your sample can be defined by parameters, which is basically mean and standard deviation, as we've looked at the descriptive statistics. Again, if the data is normally distributed, then you can simply say your mean and standard deviation value, then you can pretty much represent how your whole population is distributed around the mean and standard deviation. So that's why it's called parametric test. The non-parametric test, again, it's not assuming these. So basically, you can apply it to data set that's not in interval ratio data, such as ordinal data or nominal data. And also, it doesn't require the assumptions of normal distribution. So if you plot your data set and if it turns out it's not normally distributed, although it's interval ratio, you can fall back into non-parametric test that is equivalent to the parametric test. But unfortunately, we don't have all one-to-one mapping between the parametric test and non-parametric test. So sometimes there might be no corresponding test on the non-parametric test. And in that case, some of the cases, more complicated statistics can be, there are some more complicated statistics that you either transform the data set by applying some transformation functions and making it look like normally distributed and running the test and so forth. But I won't go into that much details since we don't do those in many of the cases in HCI. So first we go through the parametric test. Parametric test is mostly about comparing means of the two or more groups. So basically, if you have collected test completion time using interface A and B, then you can calculate the mean test completion time of the two groups and compare the two. And parametric tests I described in here are mostly comparing the two mean values. And it will give you a p-value, which is for rejecting H0, which assumes the mean values are the same, or mean values are not different. So
Am I right to assume that a t-test means some equivalent is 30?
sorry?
Some equivalent 30 for
Oh, number of people you mean?
Yeah.
Participant you mean? So t-test, you can pretty much run whatever number of people, but usually, again, as a rule of thumb, around 20 is a kind of minimum number that you might want to have with the.
So you can have 10 in group A and 10 in group B? Is that fine? Or do you need 20?
That's fine. So it depends on the test. So I'll talk that one, moment. So if you have a sample, if you only have one interface and you want to compare it against it in a known standard, so let's say from a previous research, we know that typing speed of an average user is about 200 character per second, and say that's a kind of standard value that is well known in the field, then what you can do is you invent a new type of keyboard layout and test your new layout with the people, but with the participants in the experiment. But one thing you can do is if there's a known kind of standard value, such as 200 CPS I've just talked about, and if that's a kind of widely agreed average value, then it might be handy if you can just compare your one group of people using your interface and just compare that mean to the well-known mean or the standard value that has to be met. So in that case, what you can use is one sample t-test. But in many cases, HCI, there is no such standard value that much widely agreed or well-known. So again, if there is a standard that you have to meet, such as, let's say if you're doing a usability study and you want to meet your SUS score of your interface has to be higher than 70, then 70 is a kind of, that's a requirement from the client or your boss or someone. Then if you want to prove that your interface meets that standard, what you can do is run your interface with people and collect the SUS scale, and you'll have the sample SUS scales, like you've collected 10 people, SUS scales from 10 people, then what you have is only one sample, right? You don't have, you didn't have two groups using different interface, but it was only one group of people using the same interface. But since you have a standard value, which is 70 that your client or your boss wants to be met, then what you can do is use this one sample t-test and put this standard or standard mean that you want to meet, and you can compare the sample mean against this standard mean and see if those two values are different. So if in average, if it ended up like your people using your interface reported 72.5 SUS scale, then you ran one sample t-test giving 70 as a standard value, then if you printed out p-value less than 0.05, then you can claim that your interface was rated higher than the 70 since the p-value is less than 0.05. But if it was not significant, then you can still claim that it's not much different from 70, so that might be safe. But if it was significant, but your mean value was 60 or something, then the test is basically saying you're significantly different from 70, so your interface is definitely worse than the standard. Okay, so as you can see here, the inference statistics are not telling you about which one is better than which, but it's only telling about if it's different or not. So if the two given value, either standard value or two samples, are different or not. So it's always deciding whether if it's different or not, then you'll have to look into descriptive statistics, which is mean or median, and see which one is better than which in case of there's a significant difference.
Yeah, that's how some people interpret statistics the way they suit their argument.
Mm-hmm. So that's one sample t-test, and again, this is only the case when you have a standard value that you want to meet or be above that standard or so forth. But in many cases, HCI research just doesn't fall into this category, but sometimes it's useful. In many of the cases, it's mostly about comparing two groups using different interface and see if there is a significant difference between two. And again, we are still talking about parametric test, and in that case, we have to have the data you collect should be interval ratio scale and should be normally distributed. And if you have two groups in sample, which is basically comparing two interfaces, interface A and B, and if you want to compare the mean value of the two group, then it's basically the t-test that you might want to, you'll have to use. And within the t-test, there are basically two types of t-tests again. And to differentiate from the one sample t-test we've talked before, this is called two sample t-test, but usually just called t-test. And within that two sample t-test, there are two types of t-test, which is one is independent t-test and the other is paired t-test. And the difference between two is how you allocated your subject. And if you remember how the difference between subject and within subject?
It's between doing with experience, like the experience of the users.
So between subject is
like is that one example, like if someone was a novice and someone was an expert.
Yeah. So someone is novice and someone is expert, and between subjects is basically one subject only falling into one condition. So on the other hand, within subject is if you had interface A and B, and the participants tried both of them and rated both of them or did the test using both of them, that's within subject design. And between subject design is when you've had 10 subjects and 5 of them used interface A and 5 of them used interface B. Does that make sense?
So the within subjects is if you have interface A and B and you're doing a paired test to compare the two. And between subjects is if you're comparing novice to expert users.
That could be the case, but still, if you still compare interface A and B, it's about how you allocate the participants. So say you are comparing interface A and B, and you have 20 participants. And if you're using within subject design, you are letting all the 20 participants to test A, and then do B with the same task, and collect both of the test completion time. So that's within subject. If it was between subject design, you will divide 20 participants into 10, and then 10 of them will use A, the other 10 will use B. And that inlines with what you've given an example, such as gender or expert and novice. You cannot really, one subject cannot really experience both, be both novice and expert or male and female. Although some people declare they are. But anyway, so that's why gender or their experience is usually between subject factor rather than within subject factor. But when comparing two interfaces, it depends on how you design your experiment. You can either go with asking participants to try all of the cases, or you can divide them into groups and only let them, each group, to try only one type of interface. So let's say, again, so that's, so depending on that design, whether your subject was between, assigned in a between subject manner or within subject manner, the test you use is different. And if you use a different test because maybe you made a mistake, then the conclusion might be totally different. I'll show you an example in the next slide. And let's say if there's 3 or more groups in the sample. So in this case, it's about comparing between interface, not only interface A and B, but if you have interface A, B, and C, and if you want to compare 3 of them, then in that case, you'll have to use ANOVA, which is analysis of variance. And there are many different types of ANOVAs, and we'll kind of go through them one by one. But so far, if you're comparing 3 interfaces or 3 or more interfaces, the test will be either one-way ANOVA or repeated measure ANOVA. And again, the criteria you choose between 2 is, again, whether if it's between subject design or within subject design.
Okay, if you did do 3 interfaces, to take subsets and compare 2 and then
compare 2 and then 2. Yeah, that's also okay, but we'll talk about that later. But in that case, you'll have to set the alpha level a little bit lower, because the conclusion that you want to make has. I'll talk about that later on when we get to that slide. But anyway, you can do that still, but you'll have to do some adjustments with the alpha level. Okay. So that's ANOVA, and the reason why it's called one-way ANOVA is because there's only one independent variable in this case, which is interface, although that one independent variable has multiple levels, which is 3 interfaces. So that's why it's called one-way, and you can easily imagine if there's 2 independent variables, then it's called two-way ANOVA and so forth. And we'll talk about that later on. And the case of within subject design is called repeated measure ANOVA. And by repeated measure, it means you have a subject and put into interface A, measure once, and put into interface B and measure twice, and so forth. So you repeat the measurements with one subject. So that's why it's called repeated measure. So again, these links will give you a link to a step-by-step guide to how to do this test in SPSS. And when you run this statistics, and it will print out the p-value, and how you report those results is in this way. So when you report it, your statistics variable should be in italic, which means the statistics variable differs between the tests. For instance, t-test, the statistics variable used is called t distribution. So it's basically the name of the statistical distribution they use to calculate the probability. And the ANOVA test use f distribution, so that's the variable you have to report. And by convention, make sure you make this in italic font. So basically try to make all of the variables in italic. It's even though it's not italic, readers will know that this is a statistic variable, but the reviewers might kind of point out, and at least they'll give you a minor revision as a conclusion, so that you'll have to revise them. So better make them italic in advance at the first hand. And together with the statistics variable of the test, you have to, in many of the cases, you'll have to include the degree of freedom, which is the number that represents a kind of how much of a variability it could make. I won't go into details about explaining degree of freedom because depending on statistics tools, there's different ways to calculate this degree of freedom as well. And usually the statistics tools prints out this degree of freedom value. You can just copy that value. But again, just be mindful of that there is a number called degree of freedom depending on the statistics tools you use, and you have to report that one as well. So for instance, in t-test here, this 17 is degree of freedom, which is, in this case, number of participants minus 1. for t-test. In this case, I think it's t-test for within subject design. And if it's within subject design, it's number of participants minus 2. So again, depending on your experimental design, this degree of freedom even changes. Sorry? Oh, what it actually means, if we say, for instance, if we have 10 numbers and made an average, and the degree of freedom basically means that if you know the mean, and if you know the if you decided it's the number of the values that you'll have to know to make the mean out of it. So if you had 10 numbers, or 10 people you collected, and 10 numbers, and your mean is like 7, then you know about 9 numbers, then you can easily calculate the 10th number because you know the mean. Right? So if there was 10 participants, the degree of freedom is 10 minus 1, which is 9. And again, the way it calculates it, the example I've given you is the number of participants, but ANOVA has 2 degree of freedoms, which is one depends on number of levels in your independent variable, such as in this case, I think it's 2 means there was 3 levels, which is there was 3 interfaces you've compared. So if you report 2, and then what you describe in your paper says you are comparing interface 4 interfaces A, B, and C, and D, then the reviewers say, why is your degree of freedom 2 when you have 4 interfaces and so forth? So again, so those numbers means different things depending on which statistical tool you are using.
So the 17 is really 18 users in the T?
So in this case, it's 18 users in the T if it's within subject design. If it were between subject design, the number of participants might have been 19 instead of 18 because within subject design is n minus 2, the degree of freedom. So again, I would recommend not to try to note all of those numbers, but this degree of freedom is printed out by the statistics tool. So in case you want to look into more details, then you can look up the statistics book and know how to calculate those numbers. But it's not necessary. Okay. So don't worry about that. Don't worry about that. So it's just you can think roughly that usually it depends on the number of participants and number of level you had in the independent variable.
And just the last question: did we have 2 and 27? Is 27 task completion time?
In this case, 2 is depending on the number of levels. In this case, it should be comparing 3 different cases. 27 is a combination of number of participants and the number of cases, a number of levels. So this could be because of I cannot really say. It depends on within subject or between subject design. If were within subject design, it should be n minus 1 times k minus 1, which is n represents number of people, participants, and k represents number of conditions or number of levels in that independent variable. In case of between subject design, it becomes n minus k, which is number of participants minus number of conditions. So if it was within subject design, that it means we had 30 participants with 3 conditions. If it was within subject design, you have to calculate it with the formula. So again, there are certain ways to calculate this degree of freedoms, but you don't have to be aware of them. It's not necessary. The statistics tool prints out all these values for you, but the thing that you might have to be aware of is to know that there is a value called degree of freedom, depending on your statistics tool you use, and you have to report that number as well. Because depending on this degree of freedom, what they do is they compare the number they calculated with your sample against a table, which is basically a probability distribution table, and then compare the two numbers and see if which number is bigger than which, and then and then based on that you calculate the p value. So that's why this degree of freedom is important. So, and if you've ran a t-test, then it will also print out the t value, or the value in the t statistics, and you'll have to report the t value as well. And this is basically the value calculated based on your sample. And what the statistics tool does as a next step is it compares this number against the standard t distribution table, and then calculates the p value out of it. Okay. So so again, you'll have to report the distribution the test is using. So if it was t-test, it's t distribution. If it was ANOVA, it's f distribution. And the degree of freedom, it will be printed out by the statistics tool, and it depends on the test you are doing. And then the statistics tool will also print out this number, which is either the t value for t-test or f value for the f-test. This is the value based on your sample. And then in addition, it will print out the p-value as well. So even if it doesn't print out the p-value, you can still calculate the p-value based on this. Okay, but it's more but then you'll have to look up the t distribution table and then calculate the probability. So the statistics tool does calculate the probability out of it anyway. So at the end, you'll have to, the final value you really want to show is the p-value. So if you want to just report in a very brief way, you can only report the p-value. But to be more formal, it's better to report your probability distribution, degree of freedom, and the value out of that test. And again, statistic variable might be better to be in italic. And when you're reporting p-value, since probability is always between 0 and 1, you don't really have to report write 0 at the beginning. So you can just start with 0.032. There's nothing wrong writing 0.032, but it's more concise and it's more easier to read. So that's a recommendation. And some of the journals actually require this because of their formatting guide. And when you're reporting a very small p-value, so if your statistics tool printed out like 0.0000 with 5 O's and 1 at the end, it's not necessary that you report all those zeros, but what you can make it is to make it more concise in this way, such as just mostly up to just 3 decimals, just report the p-value was less than 0.01, which there is no problem with that. Since we are just, most of the cases we are simply interested in if it's below alpha or above alpha. That's the important thing. So we can briefly make it that way. And some of the statistics tool will actually print out 0.000. But usually this is because of the rounding they did at the lower decimal point. But anyway, you can report it in this way. So that's how you report the results of the statistics. So let's dive into example. So let's say it's within subject design, and we were comparing two interface A and B, which is, let's say, 3D pointing interface. And you've collected average error in millimeters with interface A. These were the reported values, and B, these were the reported values. Of course, these are the pairs. So first subject rated A as 3 and the B as 4. The second subject reported A as had error of 4, and then B using B 6. So these are the pairs that each subject resulted in. So given this data set, can you think which, so again, it's a within subject design. So if you go 2 slides up, which test should we use? Are you, sorry?
It's between subject design.
It was within subject design. So subjects were using both of the interfaces. So it's within subject design. So what you have to do is pair t-test. Okay. So if you run a pair t-test, the statistics tool will print out the t-value with -5.24 and with degree of freedom 9. So you'll report these values, and it will also print out the p-value, which will be actually less than 0.01, which is small enough so that you can just report it this way. And in your report, you will write up like this: participants made significantly less error with interface A compared to interface B. And then you put the reason why you're saying significant is because of your t-test showed p is less than alpha, which is 0.05. And then why you can conclude it's less error with interface A is because of the mean value you've calculated is less for interface A and B. Okay? So these are the things that you write up in your report or in your thesis. And so this negative value is because of I typed in A first and B later. If you have typed in the other way around. So with the paired t-test, it's actually what it's calculating is actually calculating the difference between the 2 pairs. So it depends on which interface you put in first. But it's pretty much not a problem. But again, this was a paired t-test. What if it was between subject? Then again, the previous example was within subject, so we used paired t-test. And if it was between subjects, say we had 20 participants and we had 10 participants for interface A and 10 for interface B and collected, again, the data will be the same. But since the study design was different, we'll have to use different t-test, which is in this case an independent t-test. And as you can see here, the result will be not significant. And if you think a little bit more, independent t-test is just aggregating all the values and comparing the 2 means. But the paired t-test, what we did before, was actually comparing the difference between the 2 values for each sample. So that's why here, when it was within subject, you can see here there's a trend that B is slightly bigger than the other. But if you just aggregate them all and you don't pair them in this way, then you cannot really tell. Then the 2 mean value, which was here, again, the mean value will be the same anyway, right? So mean value here is about, the difference is about 1.6, and the standard deviation is almost 2, 3. Then you can think that if you just consider it as a separate 2 groups, then since the standard deviation is quite bigger than the difference, it will turn out it's not significant. But if it was within subject design, then what it will be looking into is the difference between the 2. And because of that, it gives you a conclusion of it's significantly different, because there's a certain trend that B is always bigger than, have a bigger error than A. So as you can see here, I think we've mentioned this earlier when we were talking about study designs. But anyway, within subject designs are more useful when you want to highlight the small differences, because as you can see here, you can get more direct comparison between the 2 interfaces rather than between subject. Again, in this case, you report so reports in a similar way, but oh, there we go. so you can, in this case, again, it's not significant. So you can report, in your report, you can say there was no significant difference found between the two interfaces, and you report the p-value and the statistics again. But
so what if, and the mean and the standard deviation, what would be the number difference to have it as a significant result between group A and group B? Does that make sense? Like before, you said it was 1.6 difference between the two means. How much of a difference would there need to be between the two?
That difference, it depends on the standard deviation you have in the sample.
Yeah.
So with independent t-test, usually if you have two mean values, and if the standard deviation plus minus standard deviation of the mean doesn't overlaps, then you can, it's actually standard error, but I'll talk about that later on. But if the standard deviation is not that bigger than the actual difference, then in that case, it might turn out significant with the independent t-test. But so that's the rough kind of ballpark that you can have a look with the standard deviation. But the actual values depends on the. Oh,
Leaking.
is it leaking?
Just inside.
Okay. Do you need a pen? I can give you a pen from here. Okay. That works. So again, depending on your experiment design, you'll have to use different tests, and you'll have to make sure it's the right test. Otherwise, your conclusion will be totally wrong. Okay? If you did a within subject design experiment and you ran independent t-test, then even if your conclusion should be significant as shown here, you might end up saying there was no significant end. So that's the wrong. Yeah, so that's totally different. So you're aware of that. And for t-test, some of the statistics tools actually ask you whether run one-tailed or two-tailed t-test, but most of the cases you can just choose two-tailed t-test. The difference is the one-tailed t-test is assuming that you know which one will be bigger than which one will have bigger mean than the other. So this is making an assumption of which one will have higher mean. But in many cases, the hypothesis you formulate in HCI is usually assuming that basically whether it's having difference or no difference, which doesn't considers which one is bigger than the other. So, and it's not assuming which one is better than the other. So in many cases, you cannot really assume. Of course, you can guess, but you cannot really make sure which one is bigger than the other. So most of the cases, you can just rely on choosing two-tailed t-test. There is a thing. So again, another example. What if we had more than two levels? Say, again, still the independent variable is type of interface. But in this case, not only interface A and B, but we had three different interfaces, A, B, and C. In this case, what would you choose to use?
A, B, and C would use within subject.
So should be, if it was within subject, it was ANOVA. If it was between subject, it should be one-way ANOVA. So again, if there's more than two levels in your independent variable, then you'll have to use ANOVA. And there are a lot of different types of ANOVA analysis. So depending on your number of independent variable and depending on your study design, again, whether if it's within subject or between subject. Again, if it was between subject, it's just simply one-way ANOVA, which means one way means one independent variable. And if it was within subject design, then you're measuring repetitively, taking one participant and measuring for interface A, and then putting it with interface B and measuring it again. So that's the repetitive measure ANOVA. Again, the two method differs similar to the t-test. The repetitive measure ANOVA is actually considering the pairs of the samples. So it's important that you make sure you type in the measures you've taken with one subject in the same line rather than mixing up the order. So, and then when you run the ANOVA will print out the F statistics with degree of freedom and the S statistics value and the p-value. So you can report in this way. And the pitfall here is ANOVA is merely showing this, if there is a significant difference between the levels, which means if there is a difference between the three as a whole, rather than showing difference between the pairs. So even if you had significant difference results with ANOVA, you can say there's a difference between the interfaces, but you cannot say if A is different from B or B is different from C or A different from C. So, sorry? You can still reject the null hypothesis, which is there is no difference between the interfaces. So still you can reject that, and you can say there is a difference, there is a significant difference between the interfaces, but you cannot really tell which interface specifically is different from the other. Okay, so eventually, if you have more than 2 levels in an independent variable, and when you run an ANOVA, you'll end up with doing a post hoc test, which is basically a pairwise test between the conditions, and that's what Robin first suggested, just doing pairwise test from the first time, from the beginning, and that's also what we can do. But the convention is do the ANOVA first, because if you had no significant result with ANOVA, then there's no use of doing a pairwise test anyway. So again, standard way is to do the ANOVA first, and if it's turned out significant with ANOVA, then you do the pairwise test. And usually the statistic tools, if it's a good enough tool, I don't think Excel does this, but at least the SPSS or R, I think R does this. I'm not sure. I haven't used R, but anyway, SPSS or SAS or sort of statistics tools will do the pairwise test automatically anyway for you. So you don't have to worry about formulating out all of the pairs and doing the test by yourself, but the statistics tool package will usually do that for you. And for ANOVA, there are different types of post hoc tests, which is pairwise test, and called 2K HSD, Chaffee, and LSD, and so forth. But usually the 2K HSD is the one mostly widely used. And they have slightly different p-values printed out with the same data set, but some of them are more conservative, some of them are more generous. But usually 2K HSD is the one that mostly chosen.
There's researchers have a ton of tricks to try and make their research.
Yeah, so all the statistics tools are invented by mathematicians who are measuring statistics. So there are still new statistics tools in development, and so the statistics tool that I mentioned today, it's not a kind of fixed tool that you might end up using 10 years later, but still these are the tools that are widely known and widely accepted as the standard tools that you use, and there is a high chance that these tools will be still used. But there might be still new tools invented or new tools published by statisticians saying this test is better than this and so forth. But anyway, that's why there are variety of pairwise post hoc tests, but still 2K HSD is most widely used one. And the link that I've given you with this slide, I think it will recommend you using 2K HSD anyway. So, and because of that, it's wise to report which post hoc test you used in your report. So rather than that, saying just you did the post hoc test and the results came out this, you might better report that you used either 2K HSD for post hoc test or faithful possibilities and so on. So, but in case your statistic package, your software does this automatically, what you can do is just get all the pairs. Like if it was 3, then you can pair it like A, B, B, C, and then A, C. So there are 3 pairs, and then just run the t-test. But again, you cannot really run this t-test straightforward by using alpha level of 0.05, but you'll have to adjust the level. Because what we want to do is aggregating all these 3 tests, you want to still maintain the overall alpha level of 0.05. And in that way, it's basically reducing the alpha level for each individual test. So when you add them together, it will become 0.05. Does that make sense? So if you had 3 pairs, like if you had 3 conditions, then there are 3 pairs. So in that case, for each of the tests, pairwise test, you'll have to have the alpha level, which is 0.05 divided by 3, which is number of tests you are running. So that in the end, when you end up this 0.0167 3 times, it will become 0.05, okay? So as you can see here, if you had too many levels in your independent variable, so say if you want to compare 10 interfaces, then this pairwise comparison alpha level will reduce dramatically. And in many cases, you will end up many of the pairs not having significant difference, and you'll end up like you'll need more participants to make the standard deviation smaller and so forth. So it's more recommended to have not too many levels in one independent variable. So I would definitely recommend no more than 3 levels in one independent variable. 4 could be kind of a borderline, but you might end up finding no significant difference between the pairs. So you might end up saying in your paper that you didn't find much meaningful results, and that's a pity. So that's that, and so that's called Bonferroni correction. That's how you adjust the alpha level when you are doing pairwise comparison. There is again, since there are many mathematicians worked on this field, there's another type of way to correct this, which is called Sidak correction, and this is considered to be slightly better, but it's pretty much the same. I think it's if you calculate this for 3 pairs, I think it will come up with it will still come up with 0.016 something or 7 something, which is pretty much the same value. So
are different corrections suited to different types of data, or is it...
I think Bonferroni correction is not good when you have too many levels. So again, if you say like 10 levels, then it will divide by 10. So it dramatically reduces the alpha level. So in that case, I think Sidak might be a little bit generous when you have too many levels in one case. But in general, in HCI research, when you have like 3 or 4 levels in one independent variable, usually they are pretty much the same value. So here's an example. So if you had 3 different types of interfaces and you ran ANOVA and it was significant, so the p-value of the ANOVA was less than 0.05, then what you'll have to do is compare them pairwise, because if you want to say this one is better than this, then you'll have to make sure these 2 are also significantly different. So what you can do is, since we have 4, oh, this is actually an error. If you had 4 samples, the pairs will be 6, because it's combination of 4 combination of 2, so it's 4, 3, 2, 1, and so it should be 6. So it's not 0.0125, but Where's the calculator? So again, as you can see here, the more level you have in your mission, it reduces quite a lot. 0.0083. So that's quite a small p number, which it might be quite challenging. I think that might be.
You have 4 results.
I'll correct the side correction later on. So anyway, side correction might be slightly generous than this. I think it was 0.1. It has to be 6 as well, so I'll calculate it later, but I'll fix it later. So anyway, so when you did the pairwise comparison, the statistics tool will print out all the p-values for pairwise comparison. In this graph, it's only showing the significant results, which is less than 0.083, which is this one, and this one. But the others did print, the tool might have printed out the p-value, but it was more than 0.083, so that was why not shown in here. So that's how you report the post-hoc test. And so far, we've been talking about only one independent variable, which was type of interface using. If you had more than one independent variable, so let's say you had type of interface, and the other one was, say, gender or age or level of experience, novice user and experienced user, expert user, and so forth, then that's 2 independent variables. And in this case, it's mostly ANOVA that you might end up using. And of course, you can separate them out and do one test for one independent variable and do another test for another independent variable. But doing this, this together with ANOVA, the benefit is you can show the interaction between the 2 independent variables, which means if you wanted to compare to 2 interfaces and you wanted to compare between the level of expertise, so with two-way ANOVA, what you can conclude is interface A was better for novice user, but interface B was better for expert user, and so forth. So the interaction between the 2 independent variable could be tested using ANOVA, multi-way ANOVA. So, but if you have more than 2, then it becomes a bit complicated, although statistical tool-wise, it's just a matter of typing another row of value and just adding another variable to the statistics tool dialog box. But the reason why it gets complicated is when you report it, it becomes quite complicated with dealing with multiple independent variables, interacting with each other with different pairs. So I would definitely not recommend to have more than 2 independent variables in your study. But in case you really have to do it, then still you can use multifactorial ANOVA. And again, depending on number of independent variables, it's called n-way ANOVA. If you had 2 independent variables, then it's called 2-way ANOVA. If it was 3-way ANOVA. Or usually if it's more than 2, then usually you just simply call it multifactorial ANOVA. And in SPSS, there's a tool called GLM, which is General Linear Model. And I think yep, there it is. So we'll go with an example of 2-way ANOVA. And with multifactorial ANOVA, you can also call it n by n ANOVA. And in this case, it's meaning there are 2 factors, with one with m levels and the other with 2 levels. Okay. So in this case, for instance, if you look into this graph, this is comparing 3 different interfaces between the gender. Okay. So that's 1 independent variable, 2 independent variable. The first one has 2 levels, and the second one has 3 levels. So that's called 2 by 3 ANOVA, or just simply two-way ANOVA, which means there are two independent variables. Okay? So as a result of running two-way ANOVA, the tool will print out basically 3 p numbers, which is one for each independent variable, which is called main effect in the tools. And the third p-value should be for interaction effects between the two. So if the interaction p-value was less than 0.05, then you can say, depending on gender, the test completion time differed between the interface. Or simply say there was a significant interaction between the gender and the interface type, so and so forth. And so here are the two links. Again, depending on whether it's an independent sample or dependent sample, you have to run different two-way ANOVA again. And again, dependent sample, which is within subject design, is again called repeated measure and so forth. So you can run those. Okay.
If it's split plot, is that also the?
It's in that case it's called mixed design, or mixed ANOVA, or so forth. Actually, I think the repeated measure guide will actually involve a step where you assign a repeated measure factor and between subject factor. So with ANOVA becoming multi way ANOVA, I think the tool statistics, most of the statistics packages usually fall down into the same statistics function in that tool. And when you define the variables or factors, which is the term used in ANOVA, you define it whether it's a within subject factor or between subject factor. So I think the second guide will have a step that you define which factor is within subject and which factor is between subject, so you can just assign them differently. Yeah. So far that was about parametric test, which was assuming the data you collected are interval ratio and it's normally distributed and has pretty much similar amount of standard deviation or variation. But in case your data doesn't meet those assumptions, which is most of the case with Likert scale rating results, or even if it was ordinal or interval, if it was not normally distributed or skewed too much or so forth, and then you can fall back to parametric test. And here are the corresponding tests you can run. For two groups between subject design, there's test called Mann-Whitney U-test, within subject Wilcoxon test, and so forth. So these are the corresponding tests to the parametric test we've talked before. So these are corresponding to t-test, and this one is for corresponding to ANOVA test. These are the links. Again, as you can see here, different from parametric test, which was both called t-test. Both these tests have totally different names, so you can easily imagine it was invented by totally different people, and the variables used, statistics variable used in these tests are totally different. So, for example, Mann-Whitney U test has a U statistics variable, so when you report it, you have to report the U value and so forth. So all these guides will show you how to report those statistics results. So please have a read when you use them. And again, with 3 or more groups or 3 or more levels in your independent variable, you'll still have to run post-hoc test. But unfortunately, there is no automatic. Many of the statistics tool doesn't run automatically these post-hoc tests automatically for non-parametric tests. So you'll have to do it manually by running the 2-group test in a pairwise manner. And again, you'll have to adjust the alpha level using von Ferrigno or Sidak correction when you are doing pairwise comparison. So for example, let's say we had a between subject experiment and collected SUS system usability scale, which is a little bit of debate whether it's ordinal or interval. But as I've told you last time, it's strictly saying it has to be considered as ordinal data. So in this case, you cannot use the parametric test. So since it was between subject design and comparing two groups, so as you can see from this slide, you'll have to use the man-fit-EU test, okay? So if you run a man-fit-EU test and type in these numbers, then the result will print out the U number and the P number. It will also print out other numbers such as Z value and so forth, but usually these are enough to report. And so in the report, since the p-value is less than 0.05, which is the alpha value you might have set in your study, you can report that participants scored interface A significantly lower than interface B and report the statistics values and the median values. Maybe in this case, since it's ordinal data, you can report the median value instead of mean value, so forth. So that's the corresponding test to the parametric test. There are also other non-parametric tests that might be useful for analyzing other types of data, such as, for instance, ordinal data. You can not ordinal data, nominal data. You cannot use these tests because these tests are assuming the data are at least ordinal, so that you can say which one is have higher value than the other. But ordinal data, nominal data, it's about just matter of choosing interface. So if you ask the users to choose the interface they preferred, so out of 3 or 4 interfaces, then all you end up with is number of people chosen interface A, number of people chosen interface B, and so forth, which is basically frequency. And for testing if that people chose one over the other, statistically meaningfully in a statistical way, there's a test called chi-square test, and in this test is testing the frequency distribution against the known frequency distributions and see if the two distributions are significantly different or not. And you can do this against known population frequency, expected frequency. In this case, it's called goodness of fit test, and that's how to run that. And in the other case, you can also test 2 samples and compare the two difference between the two. So for example, if you had 3 interfaces and 2 groups of novice and experts, and you wanted to compare if the interface preferred by novice is different from interface preferred by experts, then you can use the second test, which is comparing the frequency distribution of the 2 groups, which is novice and expert. The assumption is the number in the expected frequency should be not too small. Usually should be more than 5. So if so it's better to have more participants choosing the interface. So if you had only, let's say if you had 3 choices, and if you had your only 6 participants, then the frequency that might fall into each interface might be pretty much less than 5. So in that case, the chi-square test might be that reliable. So let's go with example. So let's say you ask the people to choose the preferred interface between A, B, and C. We are not considering novice or expert this time. We're just simply asking them. And then you counted the numbers, and it ended up with 17 participants choosing A, 7 choosing B, 6 choosing C. Then what you can do is run the goodness of fit test and see if this choice was random choice by chance. So by saying random choice by chance, is saying that participants just chose randomly. And if you think of doing a random choice, you can easily think that the expected outcome should be equal for each interface, right? So the expected value could be 10, 10, 10, which is maybe it's basically 30 participants. And then the observed value was 70 people chose A, 7 people chose B, and 6. This is what you observed from your sample. And this is what you are expecting, right? If it was random choice. If you ran the chi-square test, it will print out 0.02, which is less than 0.05, which means the two different distributions are significantly different. Okay? So which means observed values are different from random choice, which means this 17 people choosing A17 is not out of just random chance, but it's a meaningful result of saying people choose A more. But if it was less than, P was less than more than 0.5, then even if people chose A most, we cannot really say this is statistically significant result. But you can still report A was the most preferred interface anyway, in a descriptive way. So, okay, so I think we're almost finishing. So wrapping up, so we've talked about inferential statistics, and the outcome of the inferential statistics is always probability value or the p-value, which in many cases, meaning if there's a significant difference between the two groups or not. But it doesn't really tell us which one is better or which one is faster than the other. So you always have to report the descriptive statistic together as well, okay? So, and again, I think we've talked about this when we were talking about descriptive statistics, but whether that difference is meaningful or not depends on the application or test or the context. So for instance, where if the test completion time differed with 400 milliseconds, and if it was a critical task in nuclear control center that it's very critical to have this millisecond level of time difference, then it's a meaningful result. But even if it was significantly, the inferential statistics told it is a significant difference, and the difference was 400 milliseconds. If it was a task of like gaming, then might not be that meaningful result. So it depends on task and context. And again, when reporting descriptive statistics, it's always useful to also show some charts, such as bar charts or box plots. So usually the results with ANOVA usually just simply go with bar charts because reporting mean and standard deviation is mostly enough. But with ordinal data, it might be better to, or non-normally distributed data, it might be better to use the box plot so that people could also have the feeling of the distribution of the whole data. Okay, and with the bar chart here, you might have noticed this error bar here. This might mean sometimes standard deviation, but sometimes also standard error. And this is called error bars, but it could mean different things. So you'll have to describe what does this error bar means. So you can draw it with standard deviation. Usually the standard deviation is bigger than standard error of mean, and usually standard error of mean is preferred when you ran ANOVA or t-test, because this standard error is not only usually less than standard deviation because of it's basically dividing standard deviation by the number of roots of number of sample. It's not normally, it's not because of its smaller number so that it shows, it looks like a small variability, but the meaning itself is actually more correct to report, because standard error of mean, which means how much sample mean would differ from the population mean. So this is showing not how much difference you had, how much variance you had in your sample, but this standard error is showing this sample mean, how much it would be different in the population, the real world. So this might be more, this is in some sense is more meaningful of reporting. So that's why in many cases this error bar represents standard error. but still, it might be better to be more clear. You might be better in the caption or in your manuscript. You might be better to state that what does your error bar represents. So in the end, in your paper or your report or your thesis, you might have a section like this. Say you ran an ANOVA, so you write what statistics tool you used, such as one-way repeated measures ANOVA. You might be better to state the alpha level you used as well, and then you find the results. We found a statistical significant difference among the 3 interaction methods in terms of test completion time, and report the statistics values. And then, of course, it's ANOVA, and I think it's comparing 3 methods, so you have to run the post-hoc test. So you run the post-hoc test, showed there was a significant difference between the touch input and hand gesture, those 2 interfaces, and report the p-value. And then this is, so far it's just saying there was a significant difference between 2, but it's not saying which one took longer than the other. So you have to also say report the mean values, saying participants took more than triple amount of time. This can be phrased whatever you want. You can just simply say took more time, or if you want to emphasize the difference, you can say took twice the amount of time, or so forth, or 20% more of time, or so forth. You can write it that way, and then report the mean value and standard deviation, which is for parametric tests. And then if you have a chart, such as bar chart, then you can refer to a figure that shows the summary of the results. And if you had no significant results, then you have to report, unfortunately, in a very simple way, saying position error showed no significant difference among the 3 interfaces, and that's. So to study more, so in the research methods in HCI book, there's a chapter 4 that pretty much covers t-test and ANOVA test. So if you have a read of that chapter, you'll have some more detailed understanding of those tests. If you want to learn more about the under the hood of those statistical tests, then these tests might be a good reading, a good starting point. And it's actually not too complicated, but in many cases, you understand it once you read, but later on you kind of forget it and still confused when you come back. But still, the important thing is to know that which test you have to use when. That's the main thing you'll have to be aware of. Then once you know which test to use, then you can visit again these textbooks or the website that explains how to do it, the text with the statistics package software you have. So that's for today, and for next week, I think it will be the last lecture, and we'll be briefly going over other types of qualitative studies we didn't cover so far. So I think we'll be mainly focusing on interviews and focus groups, and we'll briefly touch case studies and ethnography, which we might not go into much detail, but we'll basically try to cover most of the rest of the book. So the assignment. So I'll give you 2 weeks, and I don't think I'll give you any assignments for next week, so this will be my last assignment. So it's pretty much what we did through the examples I've given you. So let's say you have conducted a between subject experiment. For now, I think you'll be aware of that. You'll have to make sure you notice that between subject experiment is the keyword there. And comparing 3 interfaces, yes, number of interfaces matter. And collected test completion time, this is test completion time, so it's interval ratio data. And this is how they report it. And since this is between subject experiment, you can assume that these are, since it's between subject experiment, you don't have to pair these. So each of these numbers are from different participants. Okay. So if you run the test and so choose a test that is suitable for this, and then run a test, and since it's more than 2 interfaces, you might actually also have to report post hoc test. If you are doing manually, then you have to run pairwise comparison by yourself. If you are using SPSS, it will print out the result, the pairwise comparison automatically anyway. So to run the test with this data set. The second question is actually using the same data set. What if it was a within subject design? Okay, so if it was a within subject design, you should be running the different type of ANOVA to give you a hint. And this time you have to assume that the data is the same order of participants. So this time you're assuming that these 3 values are done by the same participant. So you have to type in this value in this these 3 values in the same row when you type in for the ANOVA you used here. So that's the second thing, and you'll be surprised again how different results you will have. And sorry? SPSS, we have a license for SPSS at the lab, so I think Lee is not here with the lab anymore, so I'll mail you where on the server that the SPSS is, so you can install them. So that's the first part of an assignment. The second part of assignment is, so far I was talking about, again, I think part of your, the website guide with SPSS, I think part of it will show you how to test if these values are normally distributed or not, but for the assignment, I think you can simply assume it's normally distributed. Okay, so you don't have to run the test, but if you want to run the test, you can run it. For the second part of the assignment, this is with the Likert scale rating. So again, it's saying it's a within subject experiment, and you have 3 interfaces comparing Likert scale rating, which is ordinal data. So choose the test you have to run, and since it's more than 2 conditions, you might consider running post hoc test. This time, I'm pretty sure SPSS will not do this automatically, so you'll have to do a manual run of 2 pairs of the conditions, and of course adjust the alpha level with dividing it by the number of comparison.
3? Because you have
So
3
divide, you can. It's not because of 3. You have 3 interfaces, but it's 3 pairs. It's AB, AC, and BC. So if it was 4, it's not 4, but 6, which I made the mistake in the slides before. Okay, so and again, since it's within subject design, you can assume that these 3 pairs are done by the same participants. Okay, so that's the assignment, and I'll put this assignment on the Learn. So that's it. Slightly more than I thought, but do you have any questions so far? No, not so far, but so that's it. So the key point is to know what type of experiment design it is and what type of data it is, and then choose the correct type of statistical test, and then go to the website and follow the instructions, and then look for the p-values and the statistics numbers, and then copy and paste it to your report and type in some wording saying this one has significant difference or no significant difference, and which one was better than the other, and so forth.
So when we do our thesis and we start getting our results, the main thing to remember is just to know what type of data.
What type of data you have collected, and what type of experiment, what type of study design it is. So the main thing is either is it within subject or between subject, and the second thing is either it's ordinal, ratio, if in that case if it's normally distributed or not, and then if it's not, you have to fall back to those using ordinal. You have to consider them, treat them as ordinal data, so that you fall back into non-parametric test Okay, so that's it. Hopefully that made sense. Right. One, two, three, 1, 2, 3. 1, 2, 3, 2, 3, 4, 5, 6, 7, 8, 9, 10. A, B, C, D, E, F, G. 1, 2, 3, 4, 5, 6, 7, 8. A, B, C, D, E, F, G. Okay.